Okay, in section 1.2, we're going to be talking about integrals as general, okay, and particular solutions. So in 1.1, we differentiated a lot because we had derivatives. So now we're going to do the inverse. We're going to find integrals. And again, we've talked about general solutions, and we actually found some particular ones, or sometimes they're called unique solutions, given an initial condition. So let's say we have dy dx, right? That's our y prime, right? This is another way of writing y prime, but it's a little more specific, right? It's with respect to x. It could be with respect to t, z, r, but in this case, it's with respect to x. And in this section, so dy dx is equal to some function, okay? So the function, it could have, it could be a function of two variables, x and y. And again, this is a first order differential equation because again, the prime is, we just have one derivative. Now, this equation, or this function, takes an especially simple form if this right-hand side doesn't actually involve the dependent variable y. So if dy dx was a function just of one variable, it would simplify things. So we have this case. I mean, we could have this case that's a little more complex, but let's first start with one variable. So in other words, when you first took calculus, right, you had single variable calculus, and then you move up to multivariable calculus or vector calculus. So we want to work with this differential equation. Okay, so what happens if I integrate both sides of this equation with respect to x? So let's draw maybe my integral. I don't know. Let's make it pink, a little bit maybe darker. So if I integrate both sides, so there's my integral and there's my integral. Well, again, this guy, we really have the integral of y prime and the integral of f of x, right? But we really need a dx there. Now, the integral and y prime and y, right, these guys are inverses of each other, or specifically the derivative and the integral, so we know we're really just left with y of x. And here when we integrate a function, right, with respect to dx, we have to say dx. Could be dr, dt, in this case it's dx. But we're going to add a constant, okay, and this is actually the general, right, this is the general solution to this differential equation. And here, right, c is an arbitrary constant. Okay, so that's this is what our solutions are going to be. That's how they're going to look. And one other thing that I wanted to point out. So this is our general solution, but sometimes we like to write. So we say the integral of f of x dx. Let's maybe make it, I don't know, green. So this guy is sometimes called capital G of x, or sometimes capital F of x, but in your book it calls it capital G of x plus c. Okay, so another way of rewriting that. It's a little more succinct, but again, the G of x just means you're integrating f of x with respect to x. Okay, and finally, if we put all this together, so we started with dy dx, right? Again, just another way of writing y prime with, again, a little bit more information. and our dy dx is going to be a function of one variable, and we found this is a general solution, but we're going to want a unique or particular solution. So in order to find a particular solution, we need an initial condition. Our solution has to satisfy an initial condition. So our initial condition in this case is going to be y of some input equals an output. So we're going to say x naught and y naught, right? Where x naught represents, right, your initial start, and y naught initial start. You can think of the origin on the Cartesian plane. So that's just a quick introduction to what a general solution of a differential equation is going to look like, a particular solution, and well, we have the particular solution here because we have an initial condition. So in the next video, I'll go ahead and start doing some examples.